So if you want to do physics problems in different coordinate systems, you need to have an understanding of the unit vectors in those coordinate systems. And I actually already did the time derivatives of the coordinate system in polar coordinates, but I want to do it in spherical coordinates. So I'm going to first do it cylindrical, which is just like polar, but just to be formal about it. So let's just review. This is my x, y, and z axis. These are the Cartesian coordinates, and the nice thing about them is that I can pick any point in space. You can't really see right here, but and I can describe that in that vector in terms of a x vector. This is z, and my y one fell off. X, y, and z. And the nice thing is when I take derivatives of the unit vectors in the x, y, and z directions, they don't change. So no matter where I am, those are constant vectors. So Cartesian coordinate system is really nice in that way. But what if I use, let's use cylindrical coordinates. So in cylindrical coordinates, I can describe this point right here with this vector. And so there's three pieces of that. There's a r vector, which is the distance in the xy plane, and then an angle from the x-axis, and then a z coordinate. Okay, so here is the here is that in the xy plane, and then you just move z in the z direction. So my vector r, so let's just write this. I want to write the unit vectors, this would be r hat, and this would be theta hat, in terms of the Cartesian coordinates so that I can take derivatives, and then have z hat too. So let me first start with this. R equals, x, if I want the x coordinate from the r and theta values, it would be r cosine theta, right? Because that's my x coordinate along the x-axis. My y coordinate is going to be r sine theta, and my z coordinate is going to be z. So that means I can write the vector r as this x component, this y component, and that z component, and that'll be in Cartesian coordinates. So that's going to be r cosine theta x hat, that's my unit vector in the x direction, which does not change with time, plus r sine theta y hat plus z hat. So in the past, in the previous video, I kind of intuitively determined the direction of r hat and theta hat in terms of x hat, y hat, z hat. But for spherical coordinates, that's not so easy. So let's practice doing it in polar coordinates. So the first thing I'm going to do is take the partial. I want to see how does this r vector change with the variable r. So I'm going to take the partial of the vector r with respect to r. So if I do that, what's the partial of this term with respect to r? Well, that one doesn't depend on r. That's constant, so I just get this. So the derivative, the partial of r with respect to r is 1, so I just get cosine theta x hat. Now I need to do this one again. I have r sine theta, but the only thing that depends on r is r, so I get plus sine theta y hat. And then this one doesn't depend on r at all, so that's it. I get 0. So I get plus 0 z hat. Now, that is the direction that the vector r changes with r, but is it a unit vector? Well, in order to be a unit vector, I would need to check the magnitude of the partial of r with respect to r. So let's find that. So this is going to be the square root of cosine squared theta plus sine squared theta plus 0 squared. And cosine squared plus sine squared is 1, so I get the square root of 1, so I get 1. So this is my r hat vector. And that's what we said before. Okay. Now let's take this and let's do the same thing. I'll write it right. Actually, I think I have room. Let's do the partial of r with respect to theta. Okay, so what's the derivative of this with respect to theta? Well, r doesn't depend on theta. The derivative of cosine theta is going to be equal to, so it's going to be negative r sine theta. But then I need to also take the derivative. No, I don't. I'm taking the partial with respect to theta, so that's it. And then I get x hat. And then I have to take do it for this one, and I get plus r cosine theta y hat plus 0 z hat. And let me note here also that some people use phi, the angle phi, in polar coordinates. I like theta because when I took physics and math in college, that's what we used. And so I'm using what I used. Okay, now I need to find the magnitude of this. So let's find the magnitude of partial of r with respect to theta. That's going to be equal to, let's just write it this way. I square this term, so I get r squared sine squared theta plus r squared cosine squared theta plus 0 to the 1/2. And so the r squared factors out, and I get r, and then I have sine squared plus cosine squared is 1, so I just get r. So now to get theta hat, I just need to take, I need a new piece of paper. Yeah, this is going to go crazy, just so you know. So theta hat is going to be the partial of r with respect to theta divided by the magnitude of r, the partial of r with respect to theta. So then that makes it a unit vector because I have to divide by the magnitude. So this is r, so I get negative sine theta x hat plus cosine theta y hat. And that's equal to theta hat. And remember, why do we care? Because when I take derivatives of vectors in polar or cylindrical coordinates, I need to take the derivative of the unit vectors too. And this is one way to do it because I can take the derivatives of x hat and y hat don't change. So that's what makes it nice. So finally, let's do the partial of r with respect to z. This one's pretty easy. It's just going to be z hat, right? Because there's no z. The partial of z with respect to z is 1, and I get z hat. And so z hat is a unit vector. I don't need to find the magnitude of that. So that means that I can write the following three things. I get z hat equals z hat, theta hat equals that, and r hat equals, what did I say, cosine theta x hat plus sine theta y hat. The end. Not the end, because now we're going to do spherical coordinates. Okay. But I wanted to do it this way because it's easier to see how to do things. Spherical coordinates is much more challenging. So here's my x, y, z axis. Well, you want to remember that this is a right-handed coordinate system. So if I take the cross product of x and y, I get z. And so that's true. So you couldn't just put these any way you want. I made this out of coffee straws. Okay, so here is my vector. Here's r. So in this case, this is theta, and this angle from the z-axis, I probably should. This isn't really working. From the z-axis down here is phi. Okay, let me draw a picture like we normally draw this. So this is z hat, x hat, y hat. So that's in 3 dimensions, right? And then here is my vector. Here's my point, so that's r. This is phi. And then if I project this down into the xy plane, I get that, and that angle is theta. I know this, you really have to kind of draw these things out on your own. It does get kind of complicated. But that's what I made this for, right? So you can see here that this projection into the xy plane is how I get my coordinates. So let's write all my variables down. I shouldn't have drawn that theta right there in the middle of nowhere. So let's see. X, Z, Y, phi, project down, and that's going to be theta. Okay, so let's do my z coordinate first. Wait, what did I do in my previous case? Let's just do we're going to do it the same way. Yeah, x. So z is going to be, this is the value r. So z is easy because it's just the adjacent side of the right triangle. So it's going to be z equals r cosine phi. And remember, a lot of textbooks put this as theta and that is phi. You do what makes you happy. I'm going to do what makes me happy. You do what makes you happy. They're just variables. You can call it whatever you want. Okay, now if I project this down onto the xy plane, then this length is going to be r sine phi, right? Because it's the same as the top part, right? So that is important. Now I can use that to find my x and y coordinates. So x is going to be r sine phi times cosine of theta, and then y is going to be r sine phi sine theta. Did I do that right? I feel like, sometimes you're working on a problem, you're like, I worked this out because I knew that I'd make mistakes, and I just feel like I'm not on the right page right now. So I'm just going to double check. Okay, where'd it go? Well, I did work this out, trust me, multiple times. Okay, let's just proceed, and if I made a mistake, I'll just remake the whole video, and you guys can make fun of me later. It's already a long video. It's going to get longer. Okay. Too many papers. Okay, so next thing we want to do is to find r hat, theta hat, and phi hat. I want to find those unit vectors. So I'm going to write the vector r as r sine phi cosine theta x hat plus r sine phi sine theta y hat plus r cosine phi z hat. Now let's start with the first one. Let's say the partial of the vector r with respect to the variable r. So let's take that that partial. So right here, this is easy. I just get sine phi cosine theta x hat. This one's going to be plus sine phi sine theta y hat plus cosine phi z hat. Now I need to find the magnitude of that. So the magnitude of the partial of r with respect to r is going to be equal to, what's this stuff squared? I'm going to put it all right here. So it's going to be sine squared phi cosine squared phi theta plus sine squared phi sine squared theta plus cosine squared phi. Okay, so right here, if I factor out the sine squared phi, I get sine squared phi times cosine squared theta plus sine squared theta plus cosine squared phi. And this is equal to 1. Okay, so because this is 1, and then I get sine squared phi plus cosine squared phi is 1. So that means that this is r hat. We got one of them. Okay, now let's do phi. Let's do theta. I don't know why I just did theta. So let me write up here r equals r sine phi cosine theta x hat plus r sine phi sine theta y hat plus r cosine phi z hat. The partial of r with respect to theta. Okay, so right up here, I'm going to get the derivative of cosine is negative sine. So I can get negative r sine phi sine theta x hat. And this one's going to be plus r sine phi cosine theta y hat. And then that one has no term. Right? There's no theta in there. Okay, so now we need to find the magnitude of this. I think it should be clear, but I guess I'll do it. Partial of r with respect to theta square is going to be this squared. So it's going to be r squared sine squared phi sine squared theta plus r squared sine squared phi cosine. And actually, I'm glad I'm doing this because I did make this mistake before. Cosine squared theta. So I can factor out the r, and then I can factor out the sine squared theta. sine squared phi. And then I get sine squared theta plus cosine squared theta 1/2. This is to the 1/2. Okay, so that's 1. So I get r sine phi. That's my magnitude. So now I go back up here and I can say theta hat is equal to the partial of r with respect to theta divided by the magnitude of the partial of r with respect to theta. And if you're thinking, hey, things are getting crazy, things are getting crazy. Okay, so that means I can divide this by that, and I get negative sine theta x hat plus cosine theta y hat. I feel like that's wrong. Okay. Partial of r with respect to theta. No, that's right. Okay, good. No, that's z. That's z direction. I'm just going to double check. See, I got all this other work right here. I worked this out. No, I was trying to do the time derivatives. I did it. Let's see. R hat, partial, theta hat. Oh, that's phi. Okay, that's it. I did get that. At least I got it before. Okay. So let's write that over here, just so I have them all together. Theta hat is going to be equal to negative sine theta x hat plus cosine theta y hat. Okay. Now we need one more. And then the real fun begins, which I'm not going to do in this video. Okay, so now I want to take there's my r. The partial of r with respect to phi is going to be equal to, so here I have the partial of sine with respect to phi is going to be cosine, so I get r cosine phi cosine theta x hat. And then this one's going to be also plus r cosine phi sine theta y hat. And then this one's going to be minus r sine phi z hat. Now I need to find the magnitude. The partial of r with respect to phi magnitude is going to be equal to, can we agree that the r's are going to be in there? Yes, we can. So I'm just going to have r times cosine squared phi cosine squared theta plus cosine squared phi sine squared theta plus sine squared phi to the 1/2. Okay, so here I'm going to factor out a cosine squared, and I get cosine squared plus sine squared, and that's going to be 1. And then I'm going to get cosine phi squared plus sine squared phi squared, that's 1 too. So I get r. So that means that the unit vector, I guess I should write it up here, phi hat is going to be equal to the partial of r with respect to phi over the magnitude of the partial of r with respect to phi to make it a unit vector. And that's going to be equal to cosine phi cosine theta cosine phi cosine theta x hat plus cosine sine plus cosine phi sine theta y hat minus sine phi z hat. That's all three of them. So with those three, again, my paranoia is setting in. I did write this down. Oh, ha. Someone left me a little note on one of my scratch papers. Look, somebody loves me. I know who that was. And I love that person too. Okay, so let me just double check. Because like I said, I feel like I'm getting them wrong. And I'll probably never even say it. So, like I said, what matters, and let me just tell you, because I started to do this and I just got messed up, and I'll try it again, is to find the time derivatives. E phi cosine. Okay, I think that's right. I think because they measured from the other way. Yeah, I'm pretty sure it's right. I'm going to assume it's right. At least it's right in idea. So the key thing is when I take a derivative of phi-hat with respect to time, I can do it this way. I can take the derivatives of these with respect to time because the x, y, and z coordinates are constant. Okay, I may in the future try to make that video showing how to get the time derivatives in spherical coordinates, but I'm not going to do it right now because there's a whole bunch of other stuff to do. Peace out.